Okay, so good morning, everyone. Uh, so today we will conclude our discussion on lexical analysis component. So just to recap where we are, so the lexical structure of our programming language, it is given using a sequence of regular expressions. Regular expression R1, regular expression R2. For example, regular expression R1 could be something like int. It defines a single word, keyword, int. Okay. Similarly, regular expression R2 can be something like while, while. Okay. So on and so forth. And then you can have another regular expression for identifiers, for example. Okay. A to Z. So this is another regular expression. Okay. So like that, the whole lexical structure of your programming language is specified as a sequence of regular expressions. Okay. And this constitutes what is called as a microsyntax of your programming language, right? And then, so from this specification of the microsyntax, either you can give this microsyntax to a lexical analyzer tool such as Flex or Antlr, okay? Or you can hand code a lexical analyzer, or you can hand code a lexical analyzer. This is what is the case, okay? And how does the lexical analyzer and parser interact? So we have your lexical analyzer. Let's call lexical analyzer. We also call it as a scanner. Okay, and then we have the parser. The parser asks the lexical analyzer, could you please give me the next, sorry. Could you please give me, get next token. And the scanner responds back with the next token. Okay, so what is a token? A token has two parts. So one is a word, the other is a lexeme. For example, X is the next token is it's a tuple. So the word, the lexeme or the word is X, and its token type is ID. So that's how the scanner will respond back to the parser. Okay, so it is not the case that after the scanner is done, the parser will kick in. The parser and scanner work in a collaborative fashion, in an interactive fashion. Okay. So here, there are two disambiguation rules that we have seen in the last class. Okay. So let's say this is our program. Okay. This is our program. And floater, y, and then there is some code here, and then we have some expression, if x greater than or equal to y, do something, okay, so on and so forth. This is how it is like. So now let's say your current input pointer is here, okay, if the current pointer is here, that is the text prior to that pointer is already consumed by the scanner, and the parser asks the scanner, could you please pass me the next token? So what the scanner does is it tries to extract the longest matching prefix. What is the first rule? Extract the longest matching prefix. That is the rule. So here, so if you don't apply this rule, then like for example, the character F itself can form a token because it's a valid identifier. Similarly, the character L itself can form a token because it is described by the regular expression associated with the identifier token type. Okay, but when we apply this rule that extract the longest matching prefix, then what the scanner does is it consumes all of this float, and then there will be some regular expression here, uh, which corresponds to, let's say, the regular expression R3 here, it corresponds to float. Okay, then it says the next token is float, and it returns it back to the parser, and it is a keyword. Okay, so similarly, uh, so let's say if the pointer is here, okay, if the pointer is here, the next input pointer is here, then what happens is if the parser asks, could you please give me the next token to the scanner doesn't, it keeps going forward and it doesn't stop at float. Okay, because even after going till floater, okay, there is a regular expression which describes floater. Okay, what is that regular expression? That is identifier. Okay, so again the rule that is being applied is extract the longest matching token. So that is the rule that is being applied. Okay, and one more thing, so when there is if you, in the previous case, when the token is a float, that float is matched both by the regular expression R3 and Ri. So float, if you think of float is matched both by the regular expression R3 and Ri. So how do we resolve this ambiguity or conflict? You resolve this conflict, the ambiguity or conflict, by prioritizing the regular expression or token, which is token type, which is occurring first in the list. Okay, prioritize, that is the second rule. Prioritize the regular expression or token type occurring first in the list. These are the two rules. Okay. So now coming back to floater, so the lexical analyzer or scanner, it doesn't stop at float, okay, because it can extend float by including two more characters in the input stream, that is E and R. And then the whole thing put together, the whole word put together, it is described by the regular expression associated with the identifier token type. Okay. Now let's say the input pointer now, so the input pointer is here. Okay. So if the input pointer is here, again there are two ways of tokenizing it. One is greater than followed by equal to. So there are two ways of tokenizing it. One is you tokenize it as greater than followed by equal to, or greater than or equal to. Okay. Again, the rule that will be applied is extract the longest matching token. So what happens is greater than or equal to will be returned by the scanner as the next token type. Okay. So here in your list of regular expressions, you may have one regular expression for greater than, you may have another regular expression for equal to, you may have another expression for greater than or equal to. Okay, just because greater than is before greater than or equal to, it doesn't mean greater than has a higher precedence than greater than or equal to, because the rule that is applied here is extract the longest matching prefix. So greater than or equal to is the longest matching prefix. So this particular regular expression, is what will be used to decide what is the next token type. Okay. So this is the summary of the lexical structure or microsyntax specification, and what are the two disambiguation rules that are generally applied. Okay. So now what we will do is, and then we have seen, let's, in the last class, so given a regular expression R1, so we are given a regular expression R1, and let me use a different So given a regular expression R, we want to construct generate a CE function is R, okay, which takes a string as input, okay, and then it either accepts it or rejects it. So it accepts it if W belongs to the language described by the regular expression R. Otherwise, this is the case. And what is the idea that we have here? We take the regular expression R and we convert this regular expression R into a non-deterministic finite automata. Okay, and then there is an algorithmic way to translate R into non-deterministic finite automata, and then we convert this NFA into a DFA, and then we convert this DFA and then what we do is we minimize the DFA. Okay, this is an optional step, but this will be useful. Then we can minimize this DFA. And then finally, what we have seen is, there will be a template code. So let's say there is this template code for any regular expression. Okay, there's a boilerplate code for any regular expression. This code will remain the same. Okay, but what changes is from this DFA, there will be a state transition table that will be generated. So this table will be accessed by this isR function. And so that's all. So the code, that isR code, okay, the function code remains the same. What changes from one regular expression to another regular expression is the state transition table. Is the state transition table. And there is another thing, that is set of final states. Set of final states. So these are the two things that change. And these two things, they are nicely encoded in a table. So the isR function code, which is a boilerplate code, it remains the same. And the only what changes from one regular expression to another regular expression is the state transition table and the set of final states. So there is an interesting question last time is, what is the time complexity of isR? Okay, so if you look at, there are two problems here. One problem here is moving from R to isR. This may not be, this is not linear, okay? This is not a linear time algorithm, because when we convert a regular expression to NFA, the size of the number of states in the NFA can grow quadratically. And when we move from NFA to DFA, the number of states may grow exponentially. So the time complexity of generating isR from R may not be linear. Okay, but what is guaranteed is the time complexity of isR is linear. Okay. So this is the story when we are working with one regular expression. Okay, we started with a simple job. Okay, but now we want to take a slightly more challenging problem. The challenging problem that we have is, let's say we have these regular expressions R1, R2, R3, so on up to K. There are K regular expressions present, and given an input string, given an input string W. So what we want to check is, we want to find out whether W belongs to the language, check whether W belongs to the language described by the regular expression R1. Then if that is the case, then you output index I. If this is the case, if check W belongs to R1, if S, okay, then output 1, index 1, indicating that the string W is described by the regular expression R1. If that is not the case, if this is no, if the answer to the above thing is no, then you go ahead and you want to check if W belongs to R2. Okay. So again, so what happens is there are two paths. So one is if this is the case, then output 2. So otherwise, if that's not the case, you go down and then you check if W belongs to the language described by R3. If yes, output 3, so on and so forth. So finally, you check if W belongs to RK. If this is the case, you output K, otherwise you reject. That means the string W is not described by any of the regular expressions listed there. Okay, so that is the last case. That is a reject case. Okay, this is the problem that we have. So how can we go about solving this problem? Of course, if you see it, this problem is not that difficult to solve. So let's see. So what is the idea here? We start with regular expression R1 and we construct from regular expression R1, we construct its NFA N1 and then we construct the DFA D1 and then from here we construct the function is R1. Okay. So similarly, we go to regular expression R2, we construct the NFA N2, construct the DFA D2, and then from there we have the function. Okay, so this is the idea. Okay, the only problem here is in this approach is so let's say the length of the string is the length of the string W is T. Then what happens is the time complexity, the worst case time complexity of this procedure, of this checking procedure is theta of kt. Okay, there are k regular expressions. Each of the time complexity of each of the functions is R1, is R2, is t, theta of t. Okay, if you just take each of these, their time complexity is theta of t. In the worst case, we may have to check all the k procedures. So the time complexity turns out to be theta of kt. So that's a problem. Okay, so we want to reduce this time complexity. So the question or problem that we have, okay, so the problem at hand is how do we reduce this time complexity of theta of kt? Okay, so we want to change this to theta of t so that we get linear time complexity. Okay, so imagine in your programming language, if there are 100 different regular expressions, then you will have a huge constant hidden here. Okay, this is a huge constant. What if k is equal to 100? So it's not good. So we want to come up with a linear time algorithm for doing this job. Okay, so what is the idea? So in order to understand this idea, okay, so we have to, there are two approaches to solve this problem. So we will take, so one approach involves understanding non-deterministic finite automata a little bit well. I know the ideas from non-deterministic automata, no, not all students are comfortable. So we take a slightly different approach where we use product of DFS approach, and that's what we will do. Okay, so what is the idea here? So let's consider two DFS. Okay, so there is a DFA D1. Okay, so this DFA D1, so there's an initial state Q0, and then there is another state Q1. And so when you're in initial state and when you see input 1, you stay back here. Similarly, this is also the same. But if you see 0, you move from state 0 to state. Yeah, similarly. So there is another DFA D2. Okay. So let's call the initial state P naught. And so in this DFA, let's say on looking at 0, you stay back here. And then there is another state P1. So we have these two DFAs here. Okay. So right now, if you ask what is the language recognized by these two DFAs, then no, like it is null because none of the states are accepting states. Okay. But you can see if Q0 is an accepting state, then the DFA D1 recognizes all strings, all binary strings with even number of zeros in it. Okay, so for example, in this case, let's say if Q0 is accepting, okay, so if Q0 belongs to F0, F0 is a set of accepting states for the DFA D1. Okay, let me use F1. So if Q0 belongs to F1, then the set of accepting states, then the language recognized by the DFA D1 is a set of all binary strings with which contain even number of zeros. Okay. Similarly, if you come here and check if P1 belongs to the set of final states associated with the DFA D2, then what happens is the language recognized by the DFA D2 is a set of all strings which contain odd number of ones in it, set of all binary strings which contain odd number of ones in it. Okay. So let's say if you want to construct a language, if you want to construct, this is the language which construct a DFA which recognizes the language L1 union L2. What is L1? L1 is the language defined by the DFA D1, and L2 is the language defined by DFA D2. Okay. So how do we go about doing it? So we can construct what is called as a product automata. In order to recognize L1 union L2, we can construct a product automata D1 cross D2. And the idea here is, so you maintain a tuple, okay? On the first tuple, okay, on the first coordinate of the tuple, you keep track of what is happening in the DFA D1, and in the second coordinate of the tuple, you keep track of what is happening in the DFA D2. So if the initial state, so DFA D1 starts in initial state Q0 and DFA D2 starts in initial state P0, and on seeing an input 0, okay, on seeing an input 0, or let's say on seeing an input 1, okay, so on seeing an input 1, so what happens is DFA D1, it moves from state Q0 to state Q0. That is, it remains in the same state. Whereas the DFA D2, which we are simulating on the second coordinate, okay, which we are simulating here on the second coordinate, it moves from state 2 P0 to P1. So this is P. Okay. So now when we are in this particular state and when we see one, you know, like, so again, if you try to simulate what is happening on the first coordinate, we are keeping track of what is happening to DFA D1. So Q0 remains in state Q0, but P1, you know, like on seeing 1, it moves from state P1 to state P0. So we go to state Q0 P, to the tuple state Q0 comma P0. Okay. So like this, if you construct this whole DFA, I'm sure you would have seen this construction in your automata theory course. Okay. Let me use an eraser. This is Q1, E0. I hope you understand this construction. So let me take a moment here and see if you have any questions. Okay, if you have any questions, you may want to unmute yourselves and ask. Okay, so here, this is the product DFA. Okay, so in order to make this, so this DFA, if you see, there are no accepting states. If you want to recognize the language L1 union L2, then the accepting state would be Q0 comma P1, Q0 comma P1. This would be the accepting state. In order to recognize the language L1 union L2 in the product automata, the accepting state. Okay, this is the, I'm using this color code. So this would be the accepting state. Okay. So this is the accepting state in order to recognize L1 union L2. Okay. So L1 union L2, the accepting state is this. Okay. Similarly, is it, did I make any mistake? I think you should tell. So let's see if in the chat, if there are any corrections. I think I made one mistake in what I said. So let's see if you can correct me. I'm not seeing chat for some reason. Okay, I have a problem seeing chat box. Can you unmute and ask if you have any questions? There is a small bug in what I said, so I want you to tell what it is. Shivani, you want to answer? What is the bug in what I said?
So on the chat, actually, someone has already written it. So I read that the state marked as the accept state, it's for intersection.
Ah, exactly. Thank you, Shivani. Okay, so thanks for also telling that someone told the same in the chat. Thank you. Yeah. So this is the state. This works if it's only for the if you are trying to recognize the language L1 intersection L2, then this is the accepting state. But we are looking for L1 union L2. So because of that, so the accepting states would be this Q naught. So this is also an accepting state. This should also be an accepting state. Okay, and this should also be an accepting state. So there are three accepting states here. Okay. So the idea here is, so in general, if you have, so moving forward, okay. So in general, so if we have K languages, okay, so we start with regular expression R1, R2, Rk. So we have NFA N1, NFA N2, NFA NK, D1, D2, DK. And from all these K DFAs, we construct a product automata, D1, D2, so on up to DK. How does the state transition function? Let's say the state transition function for D1 will be something like this, delta 1 of, so also let's use this notation that no, Q naught 1, the superscript indicates the DFA number, okay, Q naught 2. Similarly, Q naught K, these are the initial states in the DFS D1 to DK. So delta 1 of, let's say, uh, uh, let me just, okay. Yeah, so let's not worry about this. Let me directly define the, okay. So the way we want to define is delta of, uh, this is the product state, QK, comma A is equal to delta 1 of Q1, comma A, so on delta K of QK, comma A. So this is how the state transition function in the product DFA is defined. Okay, and what is the initial state of this product DFA? That is Q naught 1, Q naught 2. That is each of these tuple, each of the states along the one of each of the dimensions, they are the initial states in the corresponding DFAs. Okay. So now once we have this product DFA, so what we can do is we can construct from this, we can construct a grand unified function, okay, which what it does is it applies, it runs the string W uh, on the through the product automata, and then finally, so we start somewhere here. The function isR, what it does is it takes the input string, okay, it takes the input string W, okay. From here, we end up in some state. Let's say that state is, okay, so P1, P2, so on up to Pk. This is the product final state. Okay, and this is what your isR function now does. So finally, once it figures out that when we run the string W through this particular, from the initial state, and we end up being in the state P1, P2, Pk, this product state, then what it looks for is it checks whether P1 it belongs to is a final state in the DFA T1. So it checks if P1 belongs to the final state. Let's say F1 is a set of final states for DFA D1. If P1 belongs to the final state set of final states F1, then what it does is it outputs 1. Okay. If that's not the case, let me write it here. So from here we move to here. So the final state is P1 to Pk. Okay. So what isR function does is check if P1 belongs to F1. Okay. If this is yes, output 1. So if it is no, then you go and check if P2 belongs to F1. If it is yes, output 2. If it is no, you keep going down like this. Okay, this is what it does. So this is how we can construct we can generate the function isR. Okay. So my question for you is, by doing this elaborate procedure, are we able to reduce the time complexity of the function isR from theta of kt to theta of t? That is the question. That's the problem, right? So we want to reduce its time complexity from theta of kt to theta of t. Okay. Is it the case? It looks like the case because If you see, in order to move from here, let me use a different color. Okay, in order to move from here to here, from this state to this state, the ESR function, it took t steps, where t is the length of the string. Okay, it took t steps to move from the state, initial product state, to the state P1, P2, Pk, whatever it may be. So, but the problem is the amount of work that you are doing at each of the steps is k, because you have to find out, so what will, where will state, what will be the next state of the DFA D1 on coordinate 1. And then we have to go to coordinate 2 and then try to check what is the next state of DFA D2 on coordinate 2. So in some sense, although we are able to move from this state to this state in t steps, the amount of work that we are doing in each step is k. So the time complexity still remains kt. Okay, so that would be a kind of cheating, right? So cheating means we didn't gain much after all this effort. So is there a way to solve this problem? So I'm seeing Ayush on my screen. So Ayush, can you tell, is there a way to solve this problem?
So we can using a transition function, like not for a single DFA, different transition function. We have a transition function for the entire DFA. So we won't require k steps. So we know if these are the set of states for these are set of current states, and then we have a an input. We know the next set of states we have to go. So we don't require k transition functions. It will
Okay.
blow the states like
Okay,
it.
great, great. Nice, Ayush. So the idea here is very simple. So we need to do this only in the construction process, but once the construction is done, let's say the initial state, okay, you can map the initial state. We can use a different naming, we can come up with a different, no, you can rename the states. Like for example, the initial state Q0 1, Q0 k, you can just map it to an integer state 0. Okay. So if you see every state in this product DFA, you can map it to integers. Okay, any state. Okay, so let's say you have something P1 to Pk, you map it to some integer state, some integer. So if you see, if you take unsigned int, okay, unsigned, if you consider unsigned int in C, you can have 2 power 32 different states, 2 power 32 states we can encode. Okay, so you can do the state transition very easily. You can know just by encoding each of the product states or mapping each of the product states to an integral number. That's all. Okay. And then what happens is the amount that the k amount of work that we are doing in each step, it gets collapsed to a unit work. Okay, so that is the idea. Great. So now, so we took a huge leap and arrived at a nice way to construct the ESR function algorithmically, and the complexity of ESR function is it's a linear time algorithm. Okay, so now we'll switch to slides and stop share. Okay. Yeah. So here, one interesting problem is, like we talked about, let me, that we construct a product DFA. So if you think of a product DFA, there is one issue. Okay, so typically in our programming languages, there are many keywords, right? So what happens is, give me a moment, guys. I'm not able to write for some reason. Okay. Yeah. So if you take a, okay, should be able to write. My pen is not writing here, so I may have to use a different method. Okay, let me use this method. Okay. So here, what is happening is, let's see. Okay, so if you take DFA of yeah. So DFA of if, product DFA of while, product DFA of no, the for, times so on and so forth. There are so many keywords, and let's say if there are 20 keywords and the length of each keyword is 2, then the number of states in the product DFA, it will be at least 2 power 20. Okay.
So what you're writing is not visible.
It's not visible, huh? Really? Are you able to see the PowerPoint screen?
Yes, so the PowerPoint screen is visible. Only like some part of what you have written is visible. I mean, I'm not sure if that's a problem in my end, but can someone else also confirm?
Okay.
Yeah, it's not visible on my end too.
Uh-huh. Thank you for letting me know. Let's see what can be done. Clear all my drawings. Okay, now I think I understand what's the problem is. Eraser. Usually I should be able to annotate with my on PowerPoint. It is not working. Do I have to use any trick here? Okay, so let's go ahead. So yeah, it would be nice if I can write, but for some reason there is on PowerPoint also I'm not able to write today. Not sure exactly what's the issue. Okay, so the issue is this. Okay, let me use words and explain. So if you try to find a product DFA, and if you construct a DFA for each of the keywords and try to construct a product DFA, then what happens is the size of the resulting DFA becomes extremely large. Okay, so it's hard to handle. So one technique to solve this problem is you don't construct DFAs for the keywords. Okay, so you just have a DFA for identifier and other regular expressions, and you construct a product DFA. And so given so while at the time of tokenizing, let's say if the lexical analyzer recognizes an identifier, before it returns its token type as an identifier, what it does is it looks up into its local hash table, okay, to see if it is a keyword. Okay, if it is a keyword, then instead of returning it as an identifier, it returns it as a the corresponding keyword type. Okay, just by using this simple trick, the size of your DFA will decrease probably by a factor of 1000 or 2000 times it decrease. Okay, so yeah, so this is a very simple and nice technique using which we can reduce the number of states in the product DFA. Okay. So next is, so the story is not yet complete, okay, because the parser doesn't pass a string to the lexical analyzer and asks what its token type is, okay. It simply asks what is the, hey, could you please give me the next token? So the lexical analyzer has to do two things. Number one, it has to find the extent of the current token, okay. Like for example, in this particular case, there is float. So the lexical, so the pointer, when the parser calls the lexical analyzer to ask for the next token, the input pointer is at def. Okay. So the lexical analyzer has to figure out the extent of the current token is still the character T in the input stream. This is what is called as the extent of the token, finding the extent of the token. And then the second job is it has to find the token type. So the way the lexical analyzer finds the extent of the current token is it keeps forwarding. So it has two pointers. One is the begin pointer and the second is a forward pointer. It keeps moving the forward pointer and it keeps consuming the input characters. Okay. And finally, it will kind of land up in some trap state. Like for example, after consuming T, it doesn't stop there. It tries to consume space. But when it tries to consume space, it cannot move further in the product automata because there is no word with the structure float followed by space. So the lexical analyzer kind of gets into a trap state. So once it gets into a trap state, what it does is it retracts the forward pointer to the last accepting state in the path. And that defines the extent of the current token. Okay, so this is how the lexical analyzer tries to find the extent of the current token and the token type also. It keeps moving forward, and then once it enters the trap state, it retracts back to the last accepting state. And from that accepting state, it looks and figures out what is the token type, the current token, the token type of the current word, and then gives that particular information back to the parser. Okay, so this is the algorithm, but the idea is what I have already told you. So finally, the structure of the generated scanner is like this. So you have the input buffer, and then you have the automaton simulator, and then you have the flex compiler. What the flex compiler does is, or Antlr compiler does is, it just takes the list of regular expressions and it generates the transition table for the product automata, and that's all. So the automaton simulator all the time remains the same, depending upon depending upon the micro syntax or the lexical structure of the programming language, the associated transition table changes. That's all. Okay, this is the secret behind automatic generation of scanners. And this kind of structure where the main code, like for example, here the automaton simulator remains the same, but the transition table changes. This kind of theme we will be using in the next part of the course, that is on parsing, that is on the theory of parsing also. Okay. So now it's an important question. So the next question is, how much time does it take to extract the next token from the input stream if its length is T? all the work that we did so far in today's lecture, like we are trying to reduce the time complexity from KT to T, there the word is given, there the extent of the current token is already given. But how much time does it take to extract, to determine what is the extent of the current token? Okay. So it depends upon how much backtracking that we are doing. Like we keep forwarding. At some point when we get into the trap state, then what happens is we have to backtrack, right? So let's say that backtracking can cost us, okay? For programming languages such as C, C++, all modern programming languages, usually the amount of backtracking that we do is very minimal, or constant backtracking we may do, like maybe 1 or 2 characters backtracking we will do. But in programming languages which were designed maybe 20, 25 years back, when the theory of parsing and lexical analysis, not much clarity is there, certain weird programming constructs will be there, which make the job of scanner pretty difficult. Okay. So like, for example, if you see in this, these are the 2 examples, interesting examples. The first example is from Fortran programming language. So if you see the first statement, do 5i is equal to 1.25, so what happens in, and then if you see the statement on the right hand side, both are the same except that instead of dot or floating point, we have comma in the statement on the right hand side. So depending upon whether the floating point is there or comma is there, the way the lexical analyzer has to tokenize the input statement changes. In the first case where floating point is there, the do 5i becomes one keyword, or not keyword, it becomes an identifier because white spaces are ignored in Fortran. That will be the first token. The second token is equal to, the third token is 1.25, that is a floating point literal. On the flip side, on the right hand side, where we have comma, the way it gets tokenized is do is a keyword, 5 is a statement number, I is a variable, equal to is a operator, 1 integer literal, comma 25. Okay, so if you see on the statement on the right hand side, it gets tokenized into 7 tokens, whereas the statement on the left hand side, it gets tokenized into 3. And it all depends on the way we do the tokenization. It depends on the context, that is whether that floating point is there or comma is there. So tokenizing such statements is painful because you have to go forward, look for the context, and based on the context, you have to go back and do a different kind of tokenization. Okay, so these kinds of things are hard to do in lexical analyzers. Okay, they cost you time, and also the complexity of the lexical analyzer unnecessarily bloats up, so on and so forth. Similarly, in the example 2, so the statement on the left hand side, it is an array, it's an index. Okay, if is the name of an array, you are indexing an element with index position x, you are assigning 10 to it. So the way you tokenize it versus the way you tokenize the statement that is there on the right hand side, where it is an if statement, okay, it is different. So again, it depends on the context. The way you tokenize these 2 statements, it depends on the context. Where we have to do this context dependent tokenizing, the job of the lexical analyzer becomes difficult. You may end up paying in time complexity. You may also end up paying in terms of having complex syntactic structure, because you are specifying your microsyntax or lexical structure is not as simple. Okay, so it becomes a challenge. But in modern programming languages, we don't face these kinds of issues. Like for example, in Mini-C, the programming language you are going to design, make sure that these kinds of idiosyncrasies doesn't creep in, which make your life unnecessarily hard. Okay. So I think I will stop here. This concludes our discussion on lexical analysis. So you have seen how to design a lexical analyzer. You have seen how you can design a lexical analyzer generator. And then finally, you have seen So if you don't pay attention in designing your microsyntactic structure of your programming language well, then the lexical analyzer unnecessarily becomes complex in two ways. In the first way is, your syntactic structure looks complicated. So because of that, you have to do a lot of hard work going back and forth. Software engineering wise, it's not a good idea. Second is in terms of performance also you pay a penalty because you have to go forward and then you backtrack. And whenever backtracking is there, so a lot of work goes waste. Okay. So in these two ways, you will end up getting into trouble if you have, if your microsyntactic structure is in such a way that the way you tokenize depends on some forward context. Okay. So you should try to avoid these things. And usually these things are not there in modern programming languages, but no programming languages which were designed 30 years back, 30 years back. Uh, so they have these idiosyncrasies. So with this, I conclude today's lecture, and I'll stop recording.